Okay, so now let's move to the practice with the LWD azimuthal data. And first of all, we are interested here in the azimuthal images. So let's have a look at this well and at this curtain section and data we have. So first of all, we have the standard gamma ray here, the green curve, gamma ray. So the next track is the resistivity curve. So we can see here its propagation resistivity. We have three curves, three propagation resistivity curves. And then we have a track with the density and porosity measurements. So neutron porosity and density. Density is the red curve and the porosity is the blue curve. So obviously only one azimuthal measurement we have here is the density. So and this density azimuthal curves producing the 16 sectors image here. So you can see it in the upper track. And this is really high quality image here. And the contrast of the density of this reservoir allows to see many features. All the bed boundary, crossing all the bed boundaries, and also we probably will be able to calculate the depths based on this image. So please have a look uh, first of all to the conventional data and what the problem we have here from the geosteering perspective. So let me show you. So the problem is when we change our position inside the reservoir, uh, the conventional curve, gamma ray resistivity, density, is not helping us in any way. So it's very difficult to understand if they're the top of the bottom, or are we going close to the top, or we're going close to the bottom. Please pay attention. So here I'm going close to the bottom, and now I'm going close to the top. So it's same low resistivity, same low density, and slightly change in gamma. So it's really difficult, and especially with the high angles here, like plus minus 1 degree changing in the depth of the formation, it's very difficult to understand where exactly the borehole inside of the pay zone, and even more difficult to react before the top or bottom would be crossed. Okay, so but we have here images, and images going to help us. So now let's have a closer look to the images and how we will use them. Uh, okay, so this is the standard image log. So we can see it in a bigger scale if you want, or we can do it. We can zoom in. By the way, this is the interesting effect. It's called the bull eye effect. Once you see this bull eye effect, which means that you're scratching the bottom. Let me show you. So let's have a look. This is MD 2960. So if we go here, 2960, yes, it's exactly here, 2960. Yes. So if we switch, let me switch to the density curtain section. Okay, and look how here we just scratched the here we didn't cross, we just scratched this small density layer, and this is called the bull eye effect. Okay, so I'm going to switch back to the resistivity just because it's more comfortable to work with. Resistivity number one, number two. So 1 second, this one. Okay, so let's go back to our image, and let's try to work with this deep picking, this green sinusoid. So let me see how it works. So if I see here some feature or here, which I believe we can use as the bed boundary crossing, I can go and add the dip, and the software allows me to put this sinusoid. So the software I'm using is called e-steering, but there are many petrophysicist or borehole geology or geosync software that can have this functionality. So, and now, please pay attention here. This is my sinusoid, and depending how I put it, it will affect the calculation. So here it has the measured depth. We don't need this top of the whole angle, azimuth, we really don't need this. But you have to understand that the image is being calculated in 3D and three-dimensional space, which means if I will move this axis left or right, it will affect my calculation because the image is really calculated in the 3D. Okay. Now, the only one parameters we are interested here during the geosteering is geosteering dip, this one. Okay. So this image is minus 0.53. But now, let's have a look how much it depends based on the operator hand. For example, I can install it like this, or I can install it like this, and you see how the dip is changing. Okay. And if I will play with the scale, for example, let me put it 2.2, 2.2, apply. Now you see it slightly in a different way. So now I will put this image something like that. Okay, and that probably more accurate. So, and I'm going to add one more here, like this. Okay, so don't be confused. This image is very, very useful information, but you have to always consider the level of uncertainty it has. Okay, as we learned in the previous slide, so the accuracy of the dip calculated based on image depends on many factors. And factor number one here is the interpretation. So as I said, I can put this sinusoid exactly here, and for example, the different geologists can do it slightly here, and the dip, the geosteering dip will change. Okay, so now we have all these dips. We have these dips in the table. We can even look at this table if you want. So all the dips here with all the parameters in this table. So we can export it if you want and use in some other applications. And we can see the trend of the dips and we can filter them and etc. etc. Okay. So but what most interesting is to put these dips in the curtain section. So let's go back to the curtain section and do this. This is my curtain section. This is my track with the dips, and I go ahead and click add this group. Okay, so all my dips are now added here, so you can see it in the upper track. And also, I can go down and see that every dip here, right, is marked according to well trajectory, right? And you can pick it and see what exactly the dip here. So like you see here, this second dip or this fourth dip and fifth is slightly different from the previous. It's not ideally parallel, and that's fine because as I told you, that's the real well-bore conditions and there are lots of uncertainties here. But they obviously can see the trend here, and dip is start to deepen up, or like here, right? Now it's deepen up, now start to deep down, and etc. etc. And using this information, like here is very obvious, they have to change the dip, right? So let's say this one was minus 0.7 and this one is minus 0.3 and this one is what is this, minus 3. Okay, so the obviously we can see the trends, and the more dips we have, the more accurate will be our interpretation. Of course, you have to use this together with the other information. So it should not be in contrast too much with the gamma ray resistivity and density and porosity curves. So if you put only dips, but you don't have any correlation with the other curves, it doesn't make any sense. So the deeps have to help you in your interpretation. So they should not bias or confuse your interpretation. Okay. And here we're dealing with the density image, which is like a medium quality one. The 16 sectors, so it has fair quality, but not the best one. The best one would be the resistivity image, 56 or even 112 sectors. Or the low resolution, the worst one, low resolution, will be gamma ray, which normally has 4 or 8 sectors. And it's really, I would use only qualitative in the qualitative way, just to see if we're going up the structure or we're going down the structure. I wouldn't use the deep calculated from gamma ray image like really as the as the formation as the formation deep. Okay, and let me show you again how you do it in the qualitative way. Let's have a look here. So the track, this is the same track, right? So it was a vertical track, and you see this sad face, and this is smile face. Okay, the smile face, and then you cut your surface from bottom to top. So when you drill up stratigraphically, and the sad face is when you cut it from top to bottom, when you drill down stratigraphically. And when you put this track horizontally, right? If you put it horizontally counterclockwise, okay, counterclockwise, because beginning of the well is here, and this part is here. And if you imagine now rotate this track 90 degrees clockwise, you will see exactly the same vertical track. And now you see the smile face, sad faces, and smile faces, sad faces, smile face. And it's obvious. Look, this is all the sad faces, and you're going down to the structure. And this all smile face, and you go up to the structure. Okay, and it's not confused to go up and down in the absolute space. So it's not like going 91 degree or going 89 degrees. It's going up or down in the structure. Okay, for example, you have to go up 91 degrees and still cut down the structure, or vice versa. You can go 89 degrees and still cut up the structure, depending on the angle of the formation. Okay, and now let's move to the most exciting part, which is the 3D, how these images look in 3D. Okay, so this is the borehole cylinder. It's slightly exaggerated here just to be more visible. And this is our formation dips. So you can see how they cut, they cut the borehole diameter here, and how they really locate it in the space. Okay, so that's the well view. That's the 3D, which gives us this e-steering software, and that's kind of I wouldn't say it's very informative, right? It's like it's good to see how it really locates. Okay, so this information is not what is vital to your geosteering. I mean this 3D view, but it's really nice to have to understand what's really going on the web. Okay, so that was the practice using the LWD image. Let's summarize. In this case, we use the density LWD image of the 16 sectors, which is the medium quality image. Is better than gamma ray, but worse than resistivity image. So it's fair enough to be used in qualitative way to see if we're going up or down stratigraphically, and it's also fair enough to be used in the qualitative way. So we can calculate the dips, and with the certain, I would say, probability, this number of the value of this dip in degrees can be reasonably representing the angle of our formation. Okay, so this is it for the image practice. So let's move to the next topic. Okay, let's move to the next topic, directional drilling technology. So as I said before, so that would be good. So if you have drilling background or directional drilling background, so you probably won't see anything new in this training. But if you don't have this background, it would be good to refresh these materials because the drilling technology and logging while drilling technologies is a big part of geosteering, and it has to be really good understanding of what's going on with the BHA from the directional perspective and from the measurements LWD to be able uh, to make right decisions for the geosteering. Okay, so let's do some refreshment here. Starting with the history, just to get a big picture of how the technology was developing and where we are today. Okay, so before 1950, we had only single shot survey, which means for every survey they have to run in the hole, make a shot, make a survey, and then pull out of the hole and check the map. So you can imagine what was the well construction time, yeah, using this technology, and what was the accuracy of this. So in 1960 we had the first mud motor with the bent sub, so which means changing this bent sub we can adjust different dogleg severity for the motor and steer the well, uh, try to steer the well in the desired direction. So in 1970 they had a wireline inclination while drilling, so which means that was still wireline based, but it's already, I would say, like the grandfathers of the MWD we have right now. 1980s we have the mud motor with the adjustable bend, so this more close to what we have right now. So it was the same principles um, of the mud motor as in steering the rotary sliding mode. Okay, now 1980s, with the development of telemetry, we have the proper MWD and LWD for this moment. Okay, so now it's kind of measurements while real time, and now this leads to the horizontal well drilling in 1988. So that was the first horizontal well being drilled, and as a result, we had the first attempt to geosteering. So very quickly the industry realized that drilling as per plan is not efficient, and the wells and the result of the well is not what was expected, and they start to geosteer. So probably the most advanced area at that time was the US land, with the starting to apply some technologies. You can search, or you can find lots of papers from that time, and the attempt of this stratigraphic geosteering, of these calculations, and all this. So this kind of interesting. And even with my geosteering team, when we've been doing with the clients different researches from the early wells, from the early horizontal wells, like from 90s and etc., we could clearly see like then the well was planned in one place and was finally placed in the other. So that was the big problem of the horizontal wells of that time, because the basic calculation in production, even without any simulators, by simplified formulas in Excel, can give you the same result, that the average horizontal well promise you the production which at least 3 times bigger than the vertical or slant well in the same formation. So, and then the well being planned, the well being drilled as per plan, and it do not produce that much, right? It produce the same as vertical well, or it even produce worse, right? And the people start to question, so why would we drill these horizontal wells if they're so inefficient? And with the development of the logging while drilling technologies, with measurement while drilling technologies, the industry start to understand what really is going on. That the formation was, that the calculation was right, so everything was right, but the actual environment and the errors and uncertainties, and in 90s, of course, the resolutions of the tools was much poor what we have than what we have right now. So these horizontal wells had lots of problems. And with the first attempts of geosteering, it started to develop very fast. And finally, 1999, the first rotary steerable system, which is also changing the game in terms of length and complexity of the wells. So the wells, the horizontal wells or extended reach, especially extended reach wells, most of them were undrillable with the mud motor. And with this technology, rotary steerable system in the market, so that was the game changer to start to drill them more. Also, that's a matter of course, the modeling and calculations. But in some areas, from our experience, I can tell you that the operators believe that it's not possible to drill horizontal well more than 700 meters with the mud motor. So that was the limit in that particular environment. That was the limit to deliver the weight on beat and etc. And with rotary steerable system, so they just industry start to break the records, and you can see the wells with the 13, 15 kilometers, which like most of like lots of such wells drilled in the Sakhalin Island. You can check it in the plot. So the wells drilled by ExxonMobil with RSS with the 13 and 15 kilometer with the huge complexity coefficient at the RD well. Okay, so basically that at that moment that already technology was in place, and all this year has just been improved, right? They've been improved in the accuracy and the reliability and etc. etc. And now we have all these tools are modern at this moment. Okay, so let's move further. So there are still two main tools on the market. Is the mud motor, which is simple, reliable, and cheap, but with some limitations, and the rotary steerable system. So every big service company, almost every big service company right now offers the rotary steerable system from them. So, okay, and now we'll look a little bit into details. Let's refresh what's the difference between the principles of drilling with the mud motor, positive displacement mud motor, and rotary steerable system. So the principle of mud motor is quite simple. It has adjustable bend angle, which can be adjusted on the surface, as you can see here. While the well was planned and the required dogleg severity was calculated, the directional driller adjusts the bend on the rotary table to the required angle and just run it in hole. The most important in this process of making up BHA is correctly calculate the high side and the tool face correction, because the high side, the motor doesn't know when motor is downhole, it doesn't know where is the high side, where is low side, where is north or south. So it's all been based on this tool face level, okay, and the engineer has to calculate it correctly. And the worst failure which can be at this stage is the wrong calculated tool face correction. That would lead to the wrong direction of the well, that will lead to the pull out of the hole and the catastrophic event, probably and redrill of the well. So there is the
mud motors can be configured to every section of your wellbore: vertical, curve, and lateral. At the rig location, a rig adjustable bend housing enables change of the bend angle, which modifies the build rate the motor can achieve. The performance motor application saves wear and tear on the drill string and the vertical hole, and it allows for increased ROP. When you reach the kickoff point, a stabilized steerable motor with a higher bend enables faster kickoff from vertical when drilling the curve section of the hole. In the lateral, a steerable motor with a lower degree of bend is run into the hole. Rotating the drill string allows the bit to drill straight ahead. If you end up drilling off course, entering slide mode helps you correct the drilling trajectory and get back on target. Now let's take a look at the power sections. Hunting offers a wide range of power sections for each motor size, with the option of NBR rubber stator lobes for standard torque requirements, or hard rubber for added torque. Hunting mud motors efficiently transfer hydraulic power by rotating sealed chambers within the power section configuration, as the drilling fluid is forced through. This sealed chamber defines a power stage, which turns the rotor and drives the drill bit. Many different power section configurations are available to accommodate different drilling needs. Save time, save money, and stay in the hole longer. It's as simple as...
So I use this public video which is available on the resources. So just a good animation which shows in a simple way how the mud motor is working. Okay. So now let's move to the next technology, which is the rotary steerable system. And there are two main types of the system right now in the market. Is the system which called push to bit and the system which called point to bit. So I'm also going to use a couple of videos from the service companies, which I believe the best demonstrates how exactly this system are working. Okay, so let's have a look on them. So this is the animation of push to bit system. So let's have a look. Okay, so you can see this the pads are the movable pads which used to push the boundary of the borehole and make the BHA to steer to the opposite direction. So you can see this in this direction the pad is pushing and the tool is going to that direction. So have a look at this animation. So the good thing about RSS, so it has a connection with the surface system. You can send the downlink command, so they change the settings, and then the tool start to drill. Okay, so that was the example of the push to bit system. So again, simply saying, it has the movable pads outside of the BHA, and when the pad is pushed one side of the borehole, simply saying the BHA is steering in the opposite direction. And this is it. So that was the first generation of the tools in the market, and that's kind of reliable tool and has a huge meterage right now drill with this tool, but it also has some limitation. Especially it has limitation in the soft formations, in the unconsolidated sand, where obviously you cannot push enough from the borehole sides. Okay, and some other limitations as well. That's why the next generation of the tools, which so-called point-to-bit system, came in the market. So let's have a look at them. I also using the Halliburton video here, which is in a simple and easy way demonstrate how the point-to-bit system works. So let's have a look. Okay, so it doesn't have any pads. So this system don't have any pads. It just had the movable shuffle, which is the inside this special ring, and you will see it in the bigger zoom right now. So it's kind of inside inclination. So the tool has the inside inclination, right? And it's exactly pointing the bit to the direction it has to drill. So it don't have any parts outside of the BHA. So which means it has less limitation. It can provide us more dog-leg severity in a certain environment, and this with such a technology, the more complex wells can be drilled. Okay, so it also use downlink to connect to the tool to change the settings and to adjust them and execute to follow the desired angle of the well. And here we have a comparison between two systems that snapshot from one of the publications. So you can see it here that on the left side is the well drilled with the mud motor, and on the right side the well drilled with the rotary steerable system. And what is interesting here? So have a look at this picture. So we've seen the sum of elements before, right? So we already know what's going on here. The well profile is to build inclination here from 45 to 60 degrees. Okay, so the yellow squares is the static service. So that's the MWD static service, which officially representing the well trajectory. And this is the only one official trajectory, the blue one, which is calculated based on this static service. So this trajectory is going to all the further modeling documents and etc. And the red points here are continuous inclination, and you can see this what's going on between the surveys. Okay, so the purple points here representing the tool face, which means in this purple and gray zones, that's the sliding mode. And we see what's going on here. The BK has the natural tendency to drop the angle, and the directional driller build up the angle. So it also drops and he builds up, and drops and he builds up, right? So he do everything right, and the motor is working fine. But you can see that the real shape of the well is very different from what was measured by the static surveys. So the real shape of the well basically represented by this red dot. And you can see that the dog-leg severity here is much more than you can see on the surface. And such a shape can be a problem for the well completion. It can be a problem for well cleaning. It can potentially lead to the stack pipe or some other engineering problem. Okay, and this is to build up the inclination. And here we have the azimuth. So azimuth is don't have normally such a big changes, but still you see the yellow squares here, which representing the static survey, azimuth from the survey, and the green dot which represent the continuous azimuth. And you can see it's not that severe like with the inclination, but you still can see this fluctuation that the real shape of the well in azimuth varies more when it's on the surface. So basically the conclusion here that the shape of the real shape of the well has much more tortuosity when you really see in the in the survey trajectory. Okay, and this part is drilled with the rotary steerable system, and you can see that dogleg severity is increasing. So at this part it was 0.29 degrees per 100 feet. At this part it was 1.38 with degrees, right? Which is almost 5 times bigger than here. And this is like the maximum aggressive dogleg severity, which is 4.02 degrees and 100 feet. But no matter which dogleg we're using, the real shape of the well, the red dots, almost following uh, the trajectory, the blue trajectory from the static surface, which means that the trajectory is much more smooth and the shape is much better when we have from the mud motor. The same picture we see from the inclination and the same result we see from the edge. Okay, so that's the visual explanation why the borehole conditions with the rotary steerable system is better than with the mud motor. Okay, So let's look at this comparison. Let's in some ways summarize advantages, advantages and disadvantages of each technology. Okay, so let's let's go one by one. Number one, for the mud motor, the wellbore spiralization and macro dogleg severity is much more severe uh, than with the rotary steerable system. With the rotary steerable system, the wellbore is smooth, as you just seen on the previous slide. Okay. Now the huge difference between mud motor and the RSS, that BK is not rotating during the sliding mode. Okay, that's the whole idea of the sliding. Okay, so BK is not rotating, and this leads us to the problems with the well cleaning. Uh, give us the higher probability of the potential stack pipe. It gives us the problem to deliver weight on bead, and of course, it's reduced our ROP. And this is the main KPI every dealer is tracking, right? The rate of penetration. And in the opposite for the rotary steerable system, the BHA has the constant rotation. That's the huge advantage of the rotary steerable system. So with the constant rotation, we have more effective cutting removal, so we have better well cleaning. So as a result, we have lower probability of stack pipe or any legs and racks. We have higher rate of penetration, and also with the TAM system, we have kind of automated steering, so we can set up the drilling program inside the tool, and this will follow trajectory uh, itself, right, automatically. So that's obviously the future of the drilling is the rotary steerable system. Next one, of course, the mud motor is low cost. So there is a huge number of different mud motors on the market, produced in many countries and many manufacturers. So and it's really low cost. So easy to maintain, uh, easy to transport, and low cost. Rotary steerable system much more high in the price. Okay, so can be a few times more expensive than the mud motor for the same well. So also the big disadvantage as the mud motor don't have any electronics inside, and so it's normally increasing our distance from bit to the measurement. So the sensors are more far away from the measurement, from the bit. Okay. With the mud motor, we have closer measurements to the bit, and the mud and with the RSS. And RSS, most of RSS has some at the bit measurements, like for example gamma ray at the bit, inclination at the bit. So we don't have such an option with the mud motor. So and the last one, as we discussed already a few times, it gives us more uncertainties with drilling the well because of this uh, micro dogleg severity during rotary and sliding intervals, and to make the shape of the well with the more tortuosity and more complex shape of the well. Of course, with the smoother trajectory, uh, even with rotary steerable system, we have less uncertainties. As a result, we have the error in true vertical depth is less. The error due to the servo interpolation is less. So all these uh, uncertainties, errors, and uncertainties related to the drilling of the trajectory and to calculating trajectory are less with using the rotary steerable system. So there is no conclusion which system. Of course, technologically wise, the RSS is much better, much modern. But of course, it has to be decided which system to use based on the project economics, based on the environment, and based on the requirements. So it's just important to know the difference between two of them, and which environment is better to apply. Okay, so we from here moving to the next topic, which will be the logging while drilling. So we briefly refreshed the drilling technologies. And now we're moving to the basics of logging while drilling. And we're starting from the basic and most popular measurements, the simple and most like reliable and quite informative one, the gamma ray log. So the gamma ray log has the sensor which registers the natural radiation of the rocks. And this radiation comes from the three radioactive elements, which are potassium, uranium, and thorium. So, and all of this normally has a high content in shales. So that's why the shale has the more high natural radioactivity and less in the sand. So the simplest explanation of the gamma ray, right? It can demonstrate the how many shale formation has. So the high readings gamma ray are in shales, and low readings gamma ray are in sand. So the basically to identify your lithology can be simply done with this gamma ray log. So as I said, the three main sources of natural gamma rays found in subsurface formation are thorium, potassium, and uranium, right? So, and the most naturally occurring radiation comes from potassium, which is contained in clay minerals. Some gamma radiation comes from uranium, which probably most often occurs deposited in formations through which the ones have flowed, or thorium, which found in various clay minerals. So it's important to know that some mud system may contain potassium in the form of potassium chloride, calichlor, and this will cause the gamma ray sensor to read more, and it's quite difficult to adjust this sensor for the potassium. So some of the sensors cannot be corrected, but the modern tool allows um, to execute this correction for the gamma ray, for the potassium in the mud. In the logging while drilling and in the geosteering, gamma ray was the first curve to have, and probably till the moment the most amount of the wells are drilled with the simple gamma ray. So the gamma ray is informative enough for the correlation while drilling horizontal wells. So as you've seen in the slides of geosteering, so we can do a lot even with one gamma ray curve. Okay, so normally it has the average reading and non-azimuthal, but some of the tools has the azimuthal gamma ray. So it's kind of compared to the density, it's quite difficult to shield the gamma ray because it's reading the natural array of the formation. So it's difficult to shield it, but some of the tools has the azimuthal gamma ray, and it can be 4 or 8 sectors normally. Even they be able to provide the gamma ray images, and the most having the most high resolution is the 16 sectors. So also gamma ray is useful when you have it at the bit. So and at the bit gamma ray is a very popular measurement in the rotary steerable system, right? So almost every MWD tool right now has the gamma ray sensor inside. Also, most of the gamma ray measurements are average, so they don't separate the readings between potassium, uranium, and thorium. But there are tools that called spectral gamma ray, which allows to separate the readings for each of these radioactive elements. And this can be useful, especially in the unconventional reservoirs, like in the shale plays in the United States, for example, when the entire pay zone is the shale, right? But with the different combination of these three minerals. So when you just have one curve of average gamma ray, it don't have much changes and it's difficult to correlate. But when you have three curves with the separate reading for each of these elements, that's becoming really more useful. So, but as I said, now it's not very popular in industry. So last time we've seen it was the gamma ray, spectral gamma ray tool from the Weatherford. But I think globally it's been replaced, spectral gamma ray, by the spectrometer, like the spectrometry, the global spectrometry, which now is being provided by the modern neutron tools, which use pulse neutron generators and enable to read the spectrometry of the spectroscopy of the formation. Okay, and once again we use the gamma ray mostly for the correlation and for the identifying the sand and shale and the content of the shale and clay in the in the in the bed, in the formation bed. And now let's have a look at the detector itself. So each gamma ray sensor has the Plitau type scintillation detector, which counts natural gamma ray emitted by the formation. So let's look at the scheme with the simple explanation. So this Plitau type of detectors, which normally used in the MWG tools, consist of the thallium-doped natrium crystal optically coupled to a photomultiplier tube. Let me show. So this photomultiplier tube, okay. So the body of the photomultiplier tube is held at a high voltage, about 1000 to 3000 volt, and has D-node stages, with each held a voltage more than a preceding one. Okay, so here each has voltage more than preceding one, D-node stages. So incident gamma ray is absorbed by the natrium, and the light flash given off due to absorption reaches the cathode. Okay, once it's coming here, so it's absorbed by natrium, and the light flash is registered by this cathode, and then the light causes the photocathode to eject an electron by means of photoelectric effect. So the electrons are amplified by successive D-node stages and at this zone, right? And the light appears, it appears as a single pulse at the output of the photomultiplier tube due to a high luminous period of photocathode. So the number of pulses is going to be proportional to the gamma ray absorbed, and pulse height, as they are not, is proportional to the energy of the incident gamma ray. So just for the reference, for a given reference, the photomultiplier voltage bias is high. So why gamma ray? First of all is the simple sensors. It's available in both MWG and LWG tools. So as I said, gamma ray used to determine the proportion of clay in the formation as the kali, thorium, and uranium. The spectral gamma ray sensors always to distinguish gamma ray source and its proportion in clay. So also, as we saw, the gamma ray is excellent correlation measurement, providing response to the layer. It has relatively shallow depth of investigation, so that's why it has minimal shoulder bed effect. And also, gamma ray, it's important to understand that gamma ray is unaffected by formation fluids such as water, oil, and gas. So it only determines lithology, but not the fluid in the formation. And also important to remember that gamma ray measurements are statistical and it depend on the ROP. So the lower ROP, the better precision. But normally with the rates of penetration we've seen in the standard drilling here, up to 100 meters, for example, it's still the reading is still decent quality. Formation resistivity measurements. There are two main groups of formation resistivity measurements, and one of them is propagation resistivity tools, which based on the electromagnetic principles, and the ladder lock tools, which are based on the short circuit current circuit principle. And the big difference in terms of physics for these two methods is that when the tool scanning the formation from the physics perspective, uh, for the propagation tool, it will be resistors in parallel. Okay, so the mud filtrate, the filtrated zone, and the true formation resistivity will be as a resistor in parallel. So, and the in case of ladder lock tool, so that will be resistor in the sequence. So the same resistivity of the mud, resistivity of the invaded zone, and true formation resistivity, that will be resistivity and thickness. And from where will come the advantages, disadvantages, limitations of these measurements, which we're going to discuss more on the next slides. Yeah, I would like to once again you to pay attention to these terms. So we're going to use more like RT, true resistivity of the formation. That's in ideal case the resistivity of the resistivity without any effect of the borehole in the formation. Then we have resistivity XO, which is resistivity of the washed zone. Right, we're going to talk about these effects a little later when the mud filtrate invading the formation, and resistivity of the mud here. Okay, so let's have a look at the first group and review it in more details. So let's move to the lateral lock resistivity theory. So the lateral lock resistivity measurements are made by pushing electrical current from an electrode across the borehole and into the formation. So from the electrode to the borehole and to the formation. So and with the current returning to the electrode of the tool, the return electrode, the lateral lock current path measures the formation resistivity. Okay, so that's the simple current circuit, and measures resistivity from one point to another point, following the simple formula of the law of the Ohm. Okay, so and lateral lock current path measures the formation resistivity and series in sequence, as you've seen in the previous slide. That's why you need electric circuit to be complete. Okay, if circuit is not complete, the measurements will not be correct. Actually, will not exist the measurements. So that's why the lateral lock measurements are suitable for logging in the conductive mass and high resistive formations. Okay, so which means if we have imagine we have the conductive mud here, so the current is being pushed from the electrode, so it's passing the conductive mud and going straight to the formation, okay, and make its path. So but if you have, for example, the if you have here the highly resistive mud, like oil-based mud, current will not be able to go through this borehole with the mud, and will not be able to make its path, and the measurements will not exist. So that's very important limitation of the lateral lock resistivity tool. Okay, so simply saying, if the resistivity of the invaded zone of the formation, which I showed you on the previous slide, is much bigger than the resistivity of the true formation resistivity. So the lateral lock measurements will be very sensitive to the highly resistive zone, and not be sensitive to low resistivity uninvaded formation. Okay, so the ideal environment for this tool again is to have conductive mud like the water-based mud and highly resistive formation. So in this case, the measurements would be the better quality from this tool. Also, what is important to know for the lateral lock resistivity, so as these measurements can be focused. So it's much more difficult to focus the propagation resistivity as it has arrays. But this one has the button electrodes, which literally small buttons like less than 1 inch in diameter, and the measurements are very focused. So, and by having multiple set of these buttons and have the LWD tool to be in rotation, we're able to produce the images. And as you know from the previous slide, the exactly resistivity images, and we've been talking about the lateral lock resistivity images, have the most resolution from any LWT tools. Okay, so these measurements are very focused, has very high resolution, and will produce images of the really good quality. Now let's clarify some answers to the important questions related to physics of lateral lock resistivity tool and lateral lock resistivity theory. So what does the tool measure? The resistance measured by the tool is given by voltage drop between the return and the source, okay, um, divided by the source current. So the formula would be resistance equal um, voltage drop divided by current. Okay, just three parameters in this formula. So resistance equal voltage drop divided by current. So resistance measured by the tool in ohm meters, voltage drop between source and the return electrode in volts, and the current flowing from the source to the return electrode in amperes. So the simple school formula from the law ohm. So the resistivity, which is expressed in ohm meter of the formation, is a property of material, where the resistance expressed in the ohm measured by the tool also depends of the volume measured. So that's important to understand. So there are two uh, related by system constant called the K factor, which is the simple cases, is the length between the measurement electrodes divided by the area of the current passes through. Okay, so the resistivity, as I said, resistivity of the formation is a property of materials in ohm meters. Resistance measured by the tool, it depends of the volume measured, and the bores R capital and the R depends on the distance between electrode and the area of the current pass through. Okay, so let's move further. So in these slides, you see the formula R equal V divided by I equal R multiple L divided by S, where as we already know, R is the resistance measured by the tool, V is the voltage drop between the source and return electrodes, I is the current flowing from the source to the return electrodes measured in amperes, R is the formation resistivity in ohm meters, and L is electrode spacing in meters. S is the current flowing from the source to the return electrode in square meters. So these three parameters, the two parameters give us the spatial, describe the spatial, which we will need to calculate resistivity from the resistor. Okay, and the L divided by S is the constant for the source return electrode configuration. Okay, now let's get some visualization here. So the electrical current always follows the path of the least resistance, and it determines the shape of the current. So that's why the tools are called the conductivity seeking tools. In the homogeneous formations, the current is evenly distributed around the tool. Okay. In the layered formation, the current squeezes interconductive base, distorting the electric field. So that's important to understand. That's in homogenic formation. It distributes equal, but in the layered formation, it will tend to seek for the conductive base. And that's applicable for any resistivity measurements, like the when we go into the propagation tool theory, that's also will be true. So resistive pads have the opposite effect. The current avoids them and preferably flows in the more conductive beds. Okay, so you can see here from the left the squeeze effect and the anti-squeeze effect. So result when the measurement currents, this line, okay, follows the path of the least resistance through the more conductive layer of fracture. So this this important fact will affect all the resistivity measurements. So once we have the conductive or very conductive band, it will tend to suck all the all the current from the lateral lock resistivity tool, or as you will see later, it tend to suck the electromagnetic signal from the propagation tool and affect a lot our interpretation. For example, when we're going to talk about the inversion and the layers above the tool or below the tool, if you have one small conductive layer, so it will suck all the signal from the electromagnetic wave. It will not let you to see further. Even normally, the distance is inside the depth of investigation of your tool. Okay, so let's summarize the advantages of the lateral lock resistivity tool. So it needs the current circuit suitable for logging in conductive mass, highly resistive formations, and conductive invasion. By the way, by highly resistive formations, for example, we mean here the carbonates. The carbonates can have resistivity of hundreds and sometimes even thousands of ohm meters. And in this environment, it's very difficult to work with the propagation resistivity tool. Actually, the reading will be incorrect. So it's above the resolution of the tool. But the lateral lock resistivity tool are perfectly suitable to for the logging in very resistive beds. But you have to remember that you need a conductive mud. Okay, so if you drill in carbonates with water-based mud, is the best environment for this tool to operate. Okay. Second, the measurements are focused, which gives us the opportunity to build deformation images, which are very useful in our case, as you've seen in the previous practice example. So they're going to be useful for identification of open faults, fractures, and because of the squeeze effect. So imagine the conductive open fracture, which has the conductive mat inside, right? So it will suck all the current and will be clearly marked by the tool. Okay. Evaluation of formation resistivity at various azimuth around the borehole. So we're not when we're talking about azimuthal tool, we're not only talking about up and down. So we'll talk about 360 degrees. So we can measure left, right, top and down. So we can cover the entire borehole cylinder. And the last point is really interesting. It's called bit resistivity and geostopping. So some of the tools, so-called resistivity at the bit, they using bit as an electrode to send the current to the formation. And that will be the first point of contact with the bottom of the hole. So that's the zero blind zone, right? As we discussed before, we can have problems with the distance from the bit to the measurements, like for gamma ray it can be 15-20 meters, for survey it can be 15-20 meters. For example, for density in neutron tools, which are normally going above the telemetry in the BHA, it can be 20-25 meters, even more, right? So once you cross the any layer of feature with the sensor, which means you bit already like 30 meters inside of this zone, or outside of the zone, depending where you're going. So the bit resistivity is reading exactly at the bottom. Okay, the quality of these measurements is low. It's more quantitative measurements. It just showing if the resistivity is increasing or decreasing. It's really should not be used for the qualitative equations to calculate the saturation, how much oil, and etc. That's more for the geosteering or for the geostopping, as we see here. For example, if you drill the intermediate section of the casing, and your objective is to put the casing exactly at the top of the upcoming layer. So you can do this with this add the bit resistivity tool. For example, once you touch it with the bit, you see this reading on your logs, and you immediately stop, pull out of the hole, and run the casing. So that's kind of manipulations are called geostopping. Now let's have a look to the real example, to another real example of the images at this correlation panel. Okay, here we have gamma ray and the rate of penetration. Here we have resistivity, we have U curves, button, ring, and bit resistivity. So bit resistivity, as we just discussed, resistivity at the bit. Button is the normal lateral lock resistivity, can be different buttons with different depths of instigation, like shallow button, medium button, and deep button. So that's three buttons on the tool, and they have different depths of instigation from few inches to like 8 to 10 inches. And ring resistivity is not azimuthal. The electrode is literally the ring, and this is considered to be the most accurate. It's not azimuthal, but it's the most accurate measurements, which can be used as a true formation resistivity and used for petrophysical evaluations and saturation calculation, oil volume in the place, etc., etc. So what do we have? This is the image. You already know how to read the image. So we see the set face here, which means we cut some structure from top to bottom. And this is actually one of the way to display those images. It's called tadpole visualization. So you have the image in degrees in this scale, and you have the tadpole looking at the azimuth of the image. Okay, and look how different the features are visible on these three images from shallow to deep button. And for comparison, here you have the gamma ray image, and you can see that almost no features is visible here. At the same time, then the resistivity image shows the clear picture. Okay. So again, let's before going to the propagation resistivity, let's summarize. So lateral lock resistivity is based on the simply saying on the short circuit of the Ohm law. Okay, it's simple chain of the electrode formation and receiving electrode. So important to remember that it's suitable for the low resistivity mud and high conductive formation. So ideal environment for this tool is water-based mud and some conductive formation, some resistive formation, including high resistive with hundreds and thousands of ohm meters, like for example, carbonates. Okay, now let's move to the next topic. the theory of propagation resistivity tool. So, propagation resistivity measurements are derived from the changes in the phase, shift, and the amplitude of an electromagnetic wave as it propagates through a formation. The propagating wave induces current loops into the formation that circle the body of the local tool, blue lines here, okay? This propagation-induced current measures the formation resistivities in parallel. So electromagnetic propagation tool works best in highly conductive formations and can operate in both conductive and non-conductive mats, provided that the contrast between the mat and formation resistivity is not so high that the induced currents tend to set up in the borehole. Okay, so there is a big difference from the lateral lock resistivity tool. So this propagation tool can perfectly work in any type of the mat. And also it prefers to have a conductive formation. So the tools, each tool and its specification has limits, but normally everything above 200 ohm meters, the quality of the measurements with such a tool will be questionable. Okay, and going back to physics, so as I said, the tool has the electromagnetic coil, which induces the current, electromagnetic current going in this direction, going to the formation. And these currents, electric field, creates the secondary, it creates the first magnetic field, okay? Because the electromagnetic field is always exist like the dual, as a dual nature. And it induces this, in this direction, magnetic field. And this magnetic field induces the secondary current line and the secondary magnetic field. And how is the field is propagated, okay? So, as we discussed before, the coils and these measurements generated in information by a simple electromagnetic coil. So if you open the tool cover, you can see the simple electromagnetic coil like everywhere else. So it can be coaxial with the tool. In this case, the measurements will be average because it equally measures every part of the formation around the tool. Or the coil can be tilted, like in this case. In this case, the coil will be more sensitive to some parts of the formation when to others. And by rotating the tool and measuring these sensitivity parts, we can get the azimuthal data from the electromagnetic propagation resistivity tool. It's not the same principle as we had with the lateral lock. There you have just one electrode with the focused measurements. Here is slightly different, right? The signal is travels. It's very difficult to shield the signal. So, but using this tilted coil with the sensitive to one part of the well more than another, we can create the propagation resistivity azimuthal measurements, and even the deep azimuthal images. Of course, is not the same. It's not the same as the density or lateral lock resistivity image. So it's not. It doesn't have any quantitative value. So you can. It's very quite difficult to calculate the deep. But the advantage, they are very deep, and they can tell you what's going on if you cross the top from top to bottom or from bottom to top. So that's very useful information for geosteering as well. Now let's talk about measurements generated by propagation resistivity tool. As we just learned, actually it's never measured the resistivity of the formation, right, in comparison with the lateral lock resistivity tool. It only measures the parameters of the electromagnetic field or of the changes of electromagnetic fields. Two parameters. One, the change in the phase shift of the electromagnetic wave, how much the phase shift from the transmitter to the receiver, and the change in the attenuation of the wave. right? So the difference in the amplitude. And based on these two parameters, the resistivity curves are derived using the dielectric constant. So, which means like it's important to remember that tool never measured the true resistivity. It was like artificially calculated based on the phase shift and attenuation of the electromagnetic field. And that's why we have two set of the curves. At any electromagnetic tool, we have attenuation curves and we have phase shift curves. And as you can see here. And normally the attenuation curve has bigger depth of investigation, so they are the first one to see some event coming, but they have the poor resolution than the phase shift, so they can miss some small layers or they can average some small layers. The phase shift is different. The phase shift has sharper resolution, as you can see here, but it has less depth of investigation. So in the by doing interpretation of the set of this curve together and by knowing the physics of it, we can extract the valuable information and we can calculate the true formation resistivity. But in the most of cases, it's fair enough just to consider that one of the curves, like the second I would say medium phase shift resistivity, is really close to the true resistivity, true formation resistivity. So as you see here, the green line is the true formation resistivity. So actually it was something like 1 ohm meter, and then it's increased to almost like 20 ohm meters. And look at these two curves. So they almost never read the RT. No, they could read RT, but far away, really far away from the boundary. Okay. So in this case, you see, for example, the attenuation curve is reading low than the RT because it still feels the effect of this conductive layer here. So it's a kind of average between these two layers. Okay, phase shift, as it has less depth of investigation, is not that much affected, and it almost reads the RT of the formation. And this effect here you've seen. By the way, you see the resistivity never was given these values, okay, like 100 ohm meters. It's never existed 100 ohm meters, but artificially these values came up. So this effect is called polarization horn effect, and we'll look at it and the details on the following slides. Now let's review in more details the curve separation effect. As I told before, the curves are really tend to be affected by many factors which can happen inside of the well. So the causes for the curve separation can be divided into effects caused by drilling and effects caused by formation. Okay, so the fact that the drilling that we are drilling a hole into the formation can affect the measurements to a great extent. Rock, because rocks is replaced by the mud, okay? And this kind of disturbance can change the physics around the wellbore. As such, the two. The following presentation and following slide, I will try to put the various effects in the order of the most common, from the most common, like the mud filtrate invasion, to the last common, the least observed, which is the electric constant effect. So, however, please note that which effect can be seen depends largely on the local field and the drilling practices. So some fields will always show anisotropy, the others will always show dielectric, for example. So oil-based mud fracturing is rarely observed because it typically needs time, not time lapse to log in to appear. Okay, so basically we are dealing here with the five main effects: mud filtrate invasion, bed boundary effect, polarization, anisotropy, and the dielectric constant effect. So let's review each of them in more detail. The first one would be mud filtrate invasion. So what's happening then, as you remember in the geometry, we have the well and we have the space between the tool, between the wall of the tool and the wall of the borehole. The space will filled with the mud, okay? And with the time, the mud filtrate invades to the formation. So once it invades to the formation, it's changing the properties of the formation in the invaded zone. And here we can have two types of invasion: resistive invasion and conductive invasion. Resistive invasion is then the resistive mud invades into the conductive fluid in the formation. Like if you have oil-based mud, for example, and you have water layer, so the resistive oil will invade the formation and change the resistivity in the invaded zone. Or vice versa, you can have a conductive invasion, which means you can have the oil-based mud and the water-based mud, and you have the oil layer in the formation. And this water filtrate invading the formation and changing resistivity. So, and here the interpretation is quite logical. So, with the resistive invasion, you will see the high resistivity affecting the formation and increasing and decreasing with the distance. And with the conductive invasion, the resistivity will increase with the distance. So how we notice what's going on with the distance? By the curves with different depths of investigation. So with the propagation resistivity tool, we have always set of the curves available with the different depths of investigation and the different physics. Okay, so let's see how it looks on the logs. So with the mud filtrate invasion, if we have a resistive invasion, like the resistivity of the phase shift curves will always read the resistivity of the attenuation. And the resistivity of the short curves will read more than resistivity, more than the curves with the long space. So you can see it here. Okay, that's the resistive invasion. So the short curve reads more resistivity, which makes perfect sense, okay? Because the high resistive mud inside the formation, as you go deeper, the less resistive mud, so the less effect of it. So you see it later. You don't see it. You almost don't see it. And vice versa with the conductive invasion. So the resistivity of the phase shift curves will read less than the resistivity of the attenuation curves. And the short spacing curves will read less than the long spacing curves. That's the conductive invasion. Like here, see? And this again make the perfect sense. So let's see, we have a conductive water-based mud filling the formation, and it's showing the low resistivity on the short curves. And once you go longer to the formation, the effect is less, and we start to read more of the resistive fluid which located inside of the formation. And the longest curve will almost read through formation resistivity. Okay, of course we don't want to read the mud, we want to read the fluid of the formation, right? Because if we are logging the layer, the oil, for example, the oil saturated layer, of course we want to read the resistivity of the oil. We don't want to measure resistivity of the mud. We're not interested in it. But in case of LWD, this problem is not that severe because the time after beat, so this one parameter, so-called time after beat, is not that big. For example, if you drill with the normal ROP, right, the mud don't have much time to invade to the formation. So this effect is really not so obvious. But if you working with the wireline tools, when you log the well like one day after it was drilled, or like 48 hours after it was drilled, the effect is obvious. Okay, so you will always see the effect of the invaded formation. And from wildland culture, it was considered that the longest curve is better. Why? Because it treats the true resistivity of the formation is less affected by the invaded mud. And with the MWD is slightly different, as you will see it further, because the invasion effect is not that severe, but we have effects of the wet bond and something else and something else. And sometimes we would prefer to take the shallow curve or the medium curve, and it will read more RT. It's not affected by the invention and is not also affected by the wet bond effects. So let's move further. Right, is how you see it on the log. Is what we've just seen. This is invaded zone, right? And you can see the conductive invasion, which means the shallow curve, which are green ones, they read the basically the mud filtrate, and the longer the longer curve, it reads more oil. Okay, so it's quite obvious to pick this effect in any kind of log. For more details, so this is an interesting case from the continental Europe. So the density porosity displayed in this track is from 1.95 to 2.95, right? And this particular potential pay zone from the depths 350 to 500 meters, right? From 350 to 500 meters, 2 meters is generally considered enough resistivity to be commercial. So from 350 to 385 meters, and again from 450 to 500 meters, the phase shift measurements indicate from 1 to 1.5 ohm meters resistivity with no invasion. Okay, no invasion yet. And consider it as non-commercial, so it's not like a pay zone. So we might believe here that no invasion is probable because the density porosity is lower and may have a lower permeability. But actually resistivity inversion processing does not increase RT at all in these two zones. So the section from 385 to 450 meters has a maximum resistivity from 1 to 1.5 ohm meters, but has strong evidence of invasion. And processing does increase RT, but not to the 2 ohm meters needed for completion. So basically this entire section of formation would be overlooked with the phase shift resistivity measurements. So the deeper readings, attenuation measurements, reveal a large conductive invasion profile over the entire interval. Okay, so the deepest measurements, so in this case of this tool, this is 34 inches spacing, measures RT in the middle section, and it's above 2 ohm meters, indicating a good commercial pay zone, right? The lower zone has the deepest invasion. Inversion processing with the attenuation data increases RT above 2 ohm meters, on 2 ohm meters cutoff, once again indicating a commercial pay zone. Okay, so and the company which provided logging for this well actually is the only one company to offer to 10 depths of the borehole compressed and borehole corrected resistivity. So like the good news that we always have a good enough set of the curves to make interpretation. Yeah. So the bad news is like that volume of data can be confusing as well. So, but the calculated, let's go back to this case. So the calculated diameter of the inversion from the attenuation data is displayed as well in track number 1. And as we mentioned, the bulk density increases in the bottom zone below 450 meters, equating to the low porosity, to lower porosity. Okay, and this helps to explain the deeper inversion as a given let's call it given invasion volume. So that invades deeper in the low porosity formation. Okay, because the mud cake, probably the mud cake is controlling the invasion, not the formation. So that's kind of difficult case, but it's a good example to understand the consequence of this misreading in the log. So having just written only one curve, right? Simply saying you would miss the huge commercial pay zone, but by having proper interpretation and the software allows you to process all the curves to identify those effects, you can see that actually the formation is a good pay zone and probably contain the decent number of oil. Okay, so let's move to the next effect, which is called bed boundary effect. The bed boundary effect is more critical for horizontal wells mostly. So as we discussed before during the vertical wells and the wireline culture, so that wasn't such a problem. And for example, if you look here, these blue circles represent the focused phase shift resistivity measurements, and this green shape represents the attenuation. And if we cross the layers and perpendicular, like while vertical drilling, the reading is not giving us any problem, okay? But if we go in horizontally, like we see here, that's that black is the true resistivity. Okay, so resistivity was less and then it increased, and this yellow and blue is our phase shift resistivity and attenuation. So, and the problem is quite simple. So, for example, the big volume of investigation of the attenuation curves are reading two layers at the same time, and it's been affected. And same with attenuation, but sorry, same with the phase shift, but as they have the less depth of investigation, they're less affected by this layer. So basically, the conductive shoulder responds in the same as the resistive invasion, and resistive shoulder responds the same as the conductive invasion. So the the basic signature of these effects is looking the same. Next is the polarization. So depolarization is a part of distortion of and the uncertainties of these resistivity curves, which normally attracts the most interest. And let's have a look and see why it's happening and what can we do with it. So imagine we have two layers. So one layer has resistivity 1 ohms, and second layer has resistivity 25 ohms. And we cutting it from top to bottom with this with our PJ. Okay, so with the in this case with the inclination of 84 degrees. So what's happening here? So these two boundaries have potential difference, and the current loops are forced to cross two zones with different resistivities. So the geometrical effects at high angle is a complex, okay? So as I said, the current loops are forced to cross to two zones with different resistivities. Static charges are created, and static charges are created in the boundary. So the result is an overshoot of the tool response at the boundary between the two beds, peaking just usually inside the resistive bed. So this effect is significant only for the deep angles of a greater, for example, than 50 degrees. And then there is a sufficient resistivity contrast, a contrast between two beds, right? So the absence of polarization horns with the high contrast resistivity beds indicates that the apparent deepen angle is less than 50 degrees and vice versa. So also please note that if the tool runs along a high resistivity contrast boundary, the polarization horn can be extended over long distance. And like we see here. So let me explain it again with the more simple words. Again, you remember the picture with the current loops which are traveling to the formation around the tool, okay? So they have a different potential difference from minus to plus, in the homogeneous formation. But once you cross the layer, the exactly at the cross of the layer, the loop has additional difference in potential because one part of the loop is the minus and another part of the plus of the loop is in the plus, and it's like the boosting the electromagnetic field to fire and cross this effect. Right? It's very classic effect which you can see on every propagation resistivity tool, and it's actually it can be the sign of the approach in high resistive or conductive layer if you make the right interpretation of it. So let's look at this little analytics, how the polarization effects depend of the dip. As we already noticed that before the 50 degrees inclination, it's not even notable. So here we have vertical well. Here we have 45 degrees, and here we have the horizontal well, right? And the curve is difficult to read here, right? But the curves have different spacing from 16 to 40 inches with the different from different transmitters. And you can see that in first case we almost don't see any polarization horn effect. In the second case, we see a little of it, like just trying to demonstrate something, and with the high angle close to horizontal, the effect is maximum. That's why almost every time we're going to land horizontal well, we're going to land the section before horizontal well in the environment with the high contrast, you're going to see resistivity, you're going to see the polarization horn effects almost any time before the landing. And this can be the good, it can be used as a good tool of indication of the approach in phase zone before the landing. So let's look at the real well example here. Okay, so we have the gamma ray on the left track here, and we have resistivity curves, Borehole corrected, and we have resistivity curve not Borehole corrected. And look at this set of the curves. So obviously we're crossing. So gamma ray is showing the clean change in the lithology. So probably I would say we from the shell we enter the descent, right? And this clear indication of these curves. But exactly at the cross of the layer, it's not only increasing resistivity up to the actual resistivity of the formation, it also fires the horn, the polarization horns on the inter and on the exit. So again, you will see dealing with the high angle and horizontal wells, you will see a lot of this effect on your wells. Okay, so let's move now to anisotropy and see what it does for us and how affect our measurements to the effect of anisotropy. There are many information properties that can be anisotropic. For example, resistivity or permeability or even sonic slowness, right? So an example would be like if you wanted to slide a ruler through a stack of paper, it can slide easily if you slide it in between the layers of paper, or if you try to push it through the paper from the top. It will be very hard to do, right? It's just another example from just completely different area. So in our case, as the current traveling information around the tool in a perpendicular and a plane, so you can see that if dealing with the vertical well, the circle travels inside one formation, and dealing with the horizontal well, the circle travels all the formations here. And as we remember, the physics of the propagation resistivity measurements is the resistors in the parallel. So, and we can the effect of this anisotropy we can be calculated using this formula here. So by the formula of resistors in the parallel, okay? Just to better understanding of this effect. So how it looks like? So it will look like this. The phase shift resistivities will read higher than attenuation resistivities, and the short spacing curves will read less than the long spacing curve. Okay, so as you see it here, the short spacing read less, the long spacing read more. But at the same time, for the attenuation, the short spacing read less and the long spacing read more. So like look at this table where resistivity is changing, sorry, look at this graph where resistivity is changing from 1 ohm meters in the shale to 25 ohm meters in the sand, right? And this is 50 to 50 cent mixture. And look what's going on with the curves. So the shallow curve read less and the deeper curve read more. Okay, and this is here just for the phase shift. We have to remember that effects of anisotropy on the resistivity measurement change with the relative dip, the dip between tool and the wellbore and the resistive layers. So at low resistive dip, then the tool crosses, for example, the bed boundary at 90 degrees. So it only measures the RH, so-called RH, the horizontal component of the RT. At a high angle, it measures more and more combination of RH and RV. There is RV is the resistivity vertical component. So in case of anisotropy, we have now two components. Is the vertical component of the resistivity, of true resistivity, which is RV, and the horizontal component of true resistivity, which is RH. And notice how the effects of anisotropy don't become pronounced until 60 degrees, right, of the relative dip. So if you look back at this picture, you see that when the well was vertical, before 60, 50, 60 degrees, all curves were overlapping. No effect was noticeable. And once the dip has become bigger, we start to see this effect. Okay, it's also very important, and why we're focusing on this effect in this presentation of geosteering, because again, during geosteering, we always deal with the high angle or horizontal wells. And we're going to see lots of these effects during landing and during the drilling of the lateral section. And finally, we are moving to the last one in the row, which is dielectric constant effect. If you remember, in the beginning of the topic, when we discussed that the tool is not actually measuring the formation resistivity, it just measures the difference of phase shift and attenuation, and after it's been calculated to resistivity curves using exactly this dielectric constant, right? And what happens if this dielectric constant is not representative in this case? So we're going to get error. So let's have a look how this effect can be noticed. Okay, so it's honestly it's very rare to see. So fortunately, there are not many environments that you can see these dielectric effects. Most of the time, you don't see it. But it can happen in really high background resistivity, right? It can be like the rock dielectric properties are different from the predefined algorithm, okay, because this constant was derived empirically, and it like represent the most of the formation, but unfortunately not of them. So, and this, if the rock dielectric properties are different from what predefined in this algorithm, so we're going to see this dielectric effect. And as a result, the dielectric effect changes the tool readings and cause the curve separation. And of course, you can find all this information in the tool limit. So it will say by which limits it has to be exploited, considering the dielectric effect as well. So how you can identify this effect? So it's listed here in this slide. For example, the phase shift resistivity will read less than attenuation resistivity, and the short spacing curves will read more than long spacing curves. Okay, so like you see here in case of the phase shift, it's almost overlapping, but in case of the attenuation, the separation is different, right? So the effect is quite unique, and if normally if you cannot find, you see the separation, and you cannot find any of the four effects above, that's probably you are dealing with the dielectric effect, and you have to check this chart and see if it's really dielectric effect or not, and you can confirm it. Okay, so we're moving further. And now just a quick slide for the telemetry, because we have to remember that the main tool which transmits the data from the downhole to the surface is our telemetry tool, which is MWD, measurements while drilling. Okay, so and the main part of the transmission is the pulse generator. So in industry at the beginning, there were positive pulse system. Then, like simply saying, the system was creating was opening and closing. The valve was opening and closing the space and creating the overpressure. And this pressure steps, right, was used to code the signal. So then also what the system of the negative pulse is the same principle, but in opposite in terms of dropping the pressure. So the valve was dropping the pressure, and this steps in dropping the pressure was using to code the signal, right? So the idea is simple. Once you have any measurements downhole, now you have to code it, and now you have to send it to the surface, and you just simply using the binary system like 1010 to code the system and then send it to the surface. So normally you need to send the tool face measurements while drilling and sliding. You need to send the survey measurements once you took the survey, and of course you need to send the logging data, which is the gamma ray, for example. And the industry standard is to have at least 2 points per foot to consider the data of the good quality, right? And for this, the telemetry rate is required. So, and the first one, and the first one here and the mostly used right now in industry, it's called continuous wave. Then this impeller, here impeller together with the stator, it rotates and making the continuous wave of the pressure in the mud pressure, pump pressure, and this allows to transmit much more data to the surface using this technology. So the old tools, which around like I don't know 20-30 years around, able to produce the bit rate from 0.5 bits per second, which is barely enough to send to send the drilling data as the tool face position, for example, gravity tool face or magnetic tool face, to send the survey data once you took the survey, and it will take a while to send the survey to the surface, and gamma ray if you have, and maximum some data for resistivity curve. So, and especially if you have higher OP, you will have problem to transmit all the data. So there is the special algorithm which allows you to calculate if the bitrate would be enough or not. And this exercise is done by the telemetry engineer or MWD engineer all the time. So depends of the needs for this well. So he has to program the tool in the way the tool will be able to send all the required data. So the modern tools able to send the data in a much higher rates. It can be up to 16 bits per second. On some tools, even more than 20, 30 bits per second. Okay, as to get these rates, also some archiving algorithms are used. So to process and archive the data in a certain way, compress it, and send compress and decompress at the surface. So in this way, you can send it more. Because imagine if you work with the modern BHA, which is like triple combo, you probably have to send like the dozens of the points in the same time. And if you work with the tools which we discussed before, like deep resistivity propagation tools, only this tool will generate you like the 30-40 curves in the same time, which you have to send in real time for the processing. So we're talking about sometimes up to 100 data points to be sent to the surface. So in this case, the telemetry bitrate is really critical part of this technology. As a geosteering engineer, you just have to make sure that all your data which you required for your geosteering decisions is programmed in the tool, and it has enough bitrate to be sent with the proper data density, at least 2 points per foot. Okay, that can be done and verified on the pre-job stage. Also, we remember that the MWD tool is responsible for the DNI operation, so direction and inclination. The DNI package normally is installed inside the MWD tool and provide you the survey while you drilling according to trajectory. And we're not going to talk in details about this module today, but I would like to highlight one limitation of this model, which is called zone of exclusion. Okay, zone of exclusion is the limitation there the azimuthal system cannot properly provide the measurements, and that will affect survey. Of course, it will affect the MWD survey, but for the geosteering engineer, important to know, it will affect all the azimuthal measurements. So once the tool is lost in its direction and azimuth, so the azimuthal measurements will be wrong as well. So that's why it's also important to consider the zone of exclusion. So, for example, a declination of -5 degrees is an azimuth of 355 degrees. So therefore, here plus minus 10 degrees means 345 to 5 degrees azimuth. So for example, when deep is 56, the inclination is 90, minus 56 is 32 degrees. So therefore, plus minus results in well inclination of 24 to 44. So, however, is the combination of inclination as azimuth that must be considered, and because of that, so therefore 345 to 5 degrees azimuth and 224 to 44 inclination is let's say it's a bet for the drilling. Okay, so that's going to be zone of exclusion. Or drilling at the same azimuth like 345 to 5 degrees with the inclination 136 to 156, which is like more theoretical exercise, technically not possible. It's like drilling up to the parallel in the magnetic field vector. would be also bad for these measurements. So, however, we don't need to worry about this second case, as I said, is it virtually impossible to achieve in real environment. Okay, so if one value of inclination or azimuth is within the bad zone, while the other is not, the result is okay. That's okay. So the magnetometer measurements are only inaccurate when both lay in the bad range. Also important to note that for this example, that the drilling at the same spot but in the opposite direction azimuth, why could you also drill parallel to the Earth's magnetic field? So there is also a zone of exclusion for this case. I mean, if you are drilling at azimuth of 175 degrees, is like 180 degrees from 355 degrees calculated above. This will have a zone of exclusion of 165 to 185 degrees. So of course your inclination also has to be right. Okay, and for you to be parallel in the Earth's magnetic field, in this case, the required inclination value would be 90 plus 56, which is equal to 146 degrees. So the range of inclination that will be affected will be 146 plus minus 10 degrees. So plus minus 10 degrees, which is 136 to 156 degrees. So again, this is quite a steep inclination, and like unlikely you're gonna see it in any of your wells. So not much to worry about for the northern hemisphere minded. Big problems is drilling horizontal wells at the equator in the southward direction, and then drilling south is the southern hemisphere. Okay, so this topic seems to a little bit complex, and it's actually not out of competencies of geosteering engineer. But just make sure you know that such a limitation do exist, and during your pre-job modeling, just verify with the MWD engineer if no zone of exclusion are expected to be seen in this upcoming well. Next important group of LWD measurements of formation evaluation is density and porosity measurements, which are related normally with the radioactive sources. Okay, so this is the typical tool which contains both of the such detectors. For example, here, let me show you. So it has the gamma ray source, which normally is cesium 137, and it has near and far detectors, which collect the counts from the source, and based on the difference, they provide the matrix, the density of the matrix. And the neutron source, which is provided by americium beryllium, and it also has near far detector, and by the counts it provides the porosity measurements. Okay, so this source is responsible for density, and this source is responsible for porosity, and they're very different in the exploitation. For example, the cesium source is like it has a half of inch size, is the small button, which can be transported easily in the shield, which has the size of, I don't know, like 15-20 centimeters size shield, and the little source can be stored here and transported easily, right? So this measurement can be easily focused because it's already as a button electrode is isolated. So and we already worked in the previous example. We worked with the density images in our geosteering software. Neutron detector is quite different, so it's more difficult to shield it, and normally it's the most of the tools. It has the average readings because the array of the neutrons is the cloud of the neutrons emitting is bigger, and the source itself is more active. And if it has the size like it has the size, like, sorry for the example, like size of cucumber or banana, okay, and the shield has like almost 70-80 centimeters. It looks like a barrel, which is almost 1 meter tall and almost like 70 centimeters in diameter. So all with the anti-radioactive metal material. So this source is much more dangerous, much more active, and it's more difficult to manage and transport. So, but these two measurements together given the extremely valuable information while formation evaluation. So you instantly get the information about density, porosity, and about matrix and the fluid inside. So the gamma rays are emitted from the tool, so they interact with the formation. The returning gamma rays are measured, counts and energy levels. Okay, so that's for crazy. For the neutron, the source emit neutrons. These neutrons interact with the formations, and the amount of returning neutrons largely depend on the hydrogen present the mud in the formation. So the hydrogen only occurs in the fluid. And the hydrogen index obviously depends on the fluid and the size of the pore in which the fluid is contained. So it will be different for the gas, different for the oil, and for the water. So and obviously the hydrogen only occurs in the fluid in the pore spaces, and in the drilling mud, not in the rock matrix. Okay. So if we can accurately measure the hydrogen in the formation, then we have a measurement of porosity. The returning neutrons are counted at the detectors, and detectors count give the rate. Rate gives an idea of the neutral porosity. Let's look a little bit more details what's going on in the formation here. The cesium-137 decay is used in these sources to generate gamma ray. Is the quite similar radiation than used in the medical facilities as well. So a little bit like more details. So the following the emission of alpha or beta particle, the nucleus is left in an excited state, right? And to return it to the ground state, it might lose energy. And this is done through the emission of the very short wavelengths electromagnetic radiation, right? Of a distinct energy characteristic of the element and mode of excitation. So the radioactive isotope cesium-137 is used normally in many tools is used as a source of monoenergic gamma rays in the density logging. So actually cesi is a beta emitter as it transforms to the barium 137. So then one neutron transforms to a proton, the barium 137 nucleus is left in excited state and returns to its ground state with the emission of the gamma ray of 662 kilowatts. As the cesium is sealed inside the steel capsule, which is used for the in a normal source, the beta particle is contained, and only gamma rays are emitted further to the formation, right? So these gamma rays are normally used in the industry to determine bulk resistivity. So these gamma rays do not originate in the formation. So they normally all artificial gamma ray. So that's why not naturally occurring gamma ray. Okay. So instead, these gamma rays originate from radioactive source. This cesium, as we discussed before, which we put inside of the tool. Okay. So some more details about the gamma ray. The gamma rays have high energy, and they emitted at the speed actually as emitted at the speed of light. So naturally occurring gamma rays have energies between 0.04 and 3.2 mega electron volts, and the gamma rays are highly penetrating and may be detected after passing through several inches of the steel. So, and by measuring how this gamma ray is attenuated in the formation, the density and the photoelectric factor could be interfered. Okay, and normally it requires a thick piece of very heavy material such as lead to stop them. You can normally see in the blankets lead in shops lead blankets they used by technician to cover the source during the calibration, or to cover some parts of for the security reason. So lots of security measures, by the way, has to be, and lots of training has to be done by personnel to use with these radioactive sources. The second source of radioactive source we're talking today is the chemical neutron source, which is normally used americium 241 beryllium. So the energy emission of such a source ranges from 1 to 10 mega electron volts, with the average like 5.45. Okay, so with the same principle of unstable state, and to stabilize it emits the neutron. So in compared to, if we talk about the routine application, right? So the practical one. So the new source of neutrons and neutrons themselves much more active and danger than the gamma ray. So if the gamma ray can be stopped by the few inches of the steel, for example, right? The neutrons cannot be. So the neutrons can fire for the tens and hundreds of meters if for some reason it's emitted on the surface, and it's more difficult to shield it, more difficult to manage and to transport. So this kind of source is really always been like a point of consideration in this industry. So that's why it was a big the big advantage when the first tool appeared on the market with the instead of chemical americium beryllium, they produced the pulse neutron generator, which is the electronic source of the neutrons. So I cannot refer right now what was the first for the wireline, but for the LWD, the first one was the Echoscope from Schlumberger, which had only cesium source for the gamma ray, but for the neutron, it had a pulse neutron generator electronic device, which is much more safe and easy to use, right? So it can be start when the tool is already downhole to the required depth, so there is no risk to emit radiation on the rig floor. So this tool is really more friendly to use, right? And the latest generation of such tools, it's even completely sourceless. So the pulse neutron generator is emits in neutrons in such a high energy that it activates the formation, and the formation emits the gamma rays, which can be used to calculate density, right? And right now in the market there are tools which can be which run in the hole completely sourceless. So they just have electronic pulse neutron generator, which can be activated downhole, and no chemical source, nor cesium 137, nor americium beryllium 241 is not used in this tool. So this, of course, the big advantage for the environment and for the operating crews. So let's go back to the application of density and porosity measurements. So why would we need them in our logging while drilling and in our geosteering especially, right? So each technology we discussing in the context of geosteering today. So imagine we have only gamma ray, right? So the gamma ray can only suggest if we see the shale or the sand, simply saying, right? So it doesn't know what saturation the formation has. So to evaluate the saturation, we would need the resistivity, and we already know which type of resistivity we have and how to use them. So the resistivity can help to identify if it's a hydrocarbon, if it's a or if it's a water, right? So and the next challenge is to identify the how like how much and how recoverable this hydrocarbon here. So and which type of hydrocarbon here. And that's why we need density and the porosity. So first of all, you will see the quantitative information regarding the formation, right? What exactly density and porosity, and you will see how much it's saturated with the gas, how much it's saturated with the oil, or how much it's saturated in the with the water or the brine, right? So, and this set of measurements you see in this track in the industry called triple combo, and it's like a minimum required adequate set of the tools to make the proper petrophysical evaluation of what's going on in the formation, and also to calculate the exact parameters of the fluid, the saturation, the volume, and the oil in place. Okay. You might pay attention here to these scales. So if these scales are normal, like from 0 to 150, 0.2 to 20, that's logarithmic scale for the resistivity, very typical one. And what is interesting here, we have neutron, like a reverse scale. So we have to read it from right to left, and it has the negative uh, porosity, right? What is porosity minus 15 porosity units or minus 15%? What is it? What doesn't make any sense, right? And why do they use these scales? And here is exactly 1.90 to 2.90 uh, in the density scale, grams per cubic centimeter. So this scale is in petrophysics called compatible scales, and they designed to make the interpretation more easy and to be able to pick the particular features like the oil, gas, or gas effect or something else by eye, like in I would say on the fly, right? So let's look at the details. What are these compatible scales, and why do we need, and what's the logic behind these compatible scales? So the possible measurements range for the bulk density, for example, raw bulk, is about 1.7, from 1.7 to 3.5 grams centimeter cubic, right? So on the logs, we present a sliding window of this range of a possible bulk density measurements. So that window is standardized to a 1 gram per cubic centimeter wide. So this slide shows for common scales. Two are commonly used with the neutron-derived porosity and sandstone units, and two of them are used for the limestone transforms. Is used to determine the porosity from the neutron counts ratio measurements. So the right H value 2.65 gram per cubic centimeters and 2.71 gram per cubic centimeter correspond to the density of zero porosity sandstone and zero porosity limestone, respectively. Okay, so perhaps it's better to say the values correspond to the density of the pure minerals. Pure minerals of quartz or silicon dioxide and calcite or calcium carbonate, respectively, for the sandstone and for the limestone. Porosity calculated from the bulk density. So here the rho stands for the density or bulk density as measured by the density 2 in units of grams per cubic centimeters. By the way, except the Canada, there they prefer to present the measurements in kilograms and meter square. So it's like 2,650 kilos per grams per meter square, meter and cubic meter, instead of the more common 2.65 grams per cubic centimeter. So the rho B is the bulk density of the formation, and we must select the appropriate matrix density to convert it to density-derived porosity in the case where the correct matrix has been selected and the porosity is filled with the water only, and there is no shale in the formation. Okay. The porosity determined is correct. In other words, the apparent porosity on the log is the actual, let's say, true porosity of the formation. So the slide illustrates the relationship between density and porosity, as is explained in the following paragraphs. So the equation used here, which is you see, 1 second. Well, the equation you see here assumes the fluid water. We select the fluid water. We select sandstone or limestone matrix and the bulk density from the zone of interest. For example, if 2.65 grams per cubic centimeters and 1.65 are converted to density-derived porosity for a sandstone formation, the values would be zero porosity for 2.65 grams per cubic centimeter and 0.6 or 60 porosity units for the density value of 1.65. So the porosity as expressed as a decimal fraction of it can be multiplied by 100 porosity unit to express it as a whole number. For example, you can express it 0.6 or 60 porosity units. Okay. So this multiplication is much like multiplying the 100%, but avoid the confusion of having the units named percent. When the shale is present or the porosity in the formation contains hydrocarbons, a correction is required to the apparent porosity read on the log scale. By the way, in some regions, like the Gulf of Mexico, for example, density-derived porosity replaces density on some logs, and you see two apparent porosity scales, one based on neutron-derived porosity and the other based on the density-derived porosity. So these special presentation scales may be requested by individual operators, for example. So saying by simple words, as you see here, how we got to this compatible scale for the sandstone, because the compatible principle of compatible is clear, right? So if you have the 100% porosity, which is doesn't exist, but it means zero space for the matrix. This has the density of the fluid of the water here, which is 1. And if you have, from the other hand, 2.65, which is the density of pure sandstone, like of pure silicon, so the porosity will be 0 because it's like the pure mineral. Okay, so and the left part of this scale practically is not applicable in the oil industry. That's why we just slide it to 1.65 and relatively to 60 for the porosity. That's the simple idea behind these compatible scales. Porosity standard scales. The count ratio from the neutron tool is converted to neutron-derived porosity with a transform. So actually 3 transforms. One for the sandstone, one for the limestone, and one for the dolomite. Uh, Please remember that the counts ratio for zero porosity sandstone is different from the counts ratio for zero porosity limestone. Therefore, different transforms should be used. The transform used and indicated on the standard parameters table of the log. So all responsible log analyses refer to that parameters table because the large errors in the interpretation will result if the wrong matrix is assumed, right, and used and assumed that was used. So please recall that the neutron tool is calibrated to give the correct porosity in clean water saturated formations. In other words, the calibration is reference to the hydrogen index of fresh water and a given lithology. So when the formation contains gas, for example, the apparent neutron-derived porosity will be too low because the hydrogen index of the gas is much less than the hydrogen index of water. So we can have the same porosity range in apparent sandstone units or apparent limestone units. So the difference is in the transform used for the position of the density curve for compatibility. So we cannot tell what transform was used by simply looking at the scale numbers. So like just remember that the transform referred to above is the algorithm you selected to convert the counts ratio to apparent neutron derived porosity on the log. So to directly compare neutron density logs recorded simultaneously, they must be properly scaled. Uh, this means that under the favorable conditions of clean water filled limestone formation, the two curves will plot on the top of each other, overlay, then recorded on the compatible limestone scale. This also means that under the favorable conditions of clean water filled sandstone formation, the two curves will plot on top of each other, so they will overlay, then recorded on compatible sandstone scale. If a separation occurs between the neutral and density curves presented, then using compatible scales, it is due to at least one of 3 following conditions. First, formation lithology is not the same as that of the transform selected. Okay. Second, clay or shale is present in the formation. Uh, and the third, hydrocarbon is present in the formation, especially the gas. Just note that assume the tool is calibrated. So this one assume the tool is calibrated correctly, that the proper environment corrections were applied, and the proper stabilizer size was used in the borehole assembly while drilling. Okay. It is understood that if any of these are not correct, the curve position on the log would be shifted from the correct values. The shift could add to or partially cancel any separation from the items listed. Now, sandstone compatible scales. Sandstone matrix scales are commonly used, for example, in the area of Gulf of Mexico, in the offshore of Texas and Louisiana. So all the reservoirs in the Gulf of Mexico are sandstone, with the some exemptions in very deep wells drilled in a very deep water. So for this reason, the Gulf of Mexico is kind of a standard matrix has always been a sandstone. So the density of quartz is 2.65 grams per square centimeter per cubic centimeter, and this corresponds to zero porosity in a sandstone formation. The second scale pair represented above just the top scale pair with the both scales moved the same proportional amount to keep them match up or compatible. So this new arrangement would allow a limestone streak with the density 2.69 grams per cubic centimeters, for example, to be recorded on the log, thereas it would be off the page with the 2.65 gram per square centimeter scale. That was the maximum. Okay. The limestone compatible scales. So obviously the same logic is applies for the limestone compatible scales. So it's for the porosity it's from 60 to 0, for the density 1.71 to 1.71 to 2.71, and for the porosity 45 from 45 to minus 15, and for density 1.95 to 2.95, right? So obviously here we're never going to see the porosity from minus 15, but we need this limit to be able to see the density up to 2.95. Now let's have a look at a couple examples. And the example number one, with the compatible scale in the sandstone from the Ecuador. So the neutron and density curves overlay in the oil and in the water zone, because this is the sandstone formation, and the log is presented with the compatible sandstone scales. So in other words, the sandstone transform was used to convert the Count ratio from the neutron to neutron derived porosity, and the density scale was shifted to match it. Okay. A density of 2.65 grams per cubic centimeters corresponds to a sandstone porosity of 0 porosity units. And in oil, we sometimes see the neutron curve reading slightly less than the bulk density curve, because the hydrogen index of oil is slightly less than that of water, and because the density of oil is less than that of water. Thus, making the bulk density lower than the same formation than water field formation. However, sometimes the difference between water and oil response is not easy seen on the overlaid log curves. So it's like a very high API gravity oil, like the very light weight oil, will appear with the small gas-like separation. So what explanation would you give a client, for example, if you see no curve separation difference in the overlaid curve in the oil and water, for example? Assume the porosity in both zones is the same. So how would a different porosity in the wet and the pay zone affect the curve presentation, for example? Just please look carefully at this example. And this is different situation here. In the example number 2, let's see the difference with the non-compatible scale. So, like in the top picture here, the neutron and density curves overlay in this. Let me show you this overlay. Okay, in the sense non-compatible scale. But when presented on the line stone compatible scales, we will see the false gas effect. So please avoid this error. So if you display the data in a wrong compatible scale, the visual interpretation, which normally petrophysicists do, like picking up the gas effect on the oil or water, so just by visual tools, right? So will be wrong. So again, this is correct one, and that one is wrong. It's giving the false gas effect. So probably closing by this example, this is it for the LWD logs density neutron porosity compatible scales. Now let's move to the trajectory planning tool practice. So that exercise is just to get a little bit sense of how the geosteering engineer works with the trajectory inside the geosteering software. So, and just before moving to the practice, one important remark. So which method is used to calculate the distance between two surveys? Because all the work with the trajectory is based on this method. So before that was like the method of the average angle, medium angle, something else. Now it's not important anymore. So the industry standard is the minimum curvature method. Okay. So, and this assumes that your borehole is the arc which belongs to the sphere with the given radius. So if you have survey number 1 here and you have survey number 2 here, so the trajectory between these 2 points, it will be the arc of the sphere belongs to these 2 points. Okay, so that's the most accurate method industry has right now. But it still has lots of limitations. So as you will see in the part of drilling uncertainties. So with this remark, we go into the practice in the software. So this practical part is designed to work with the wellbore trajectory. So this part of the work to adjust and plan ahead trajectory is very important for the geosteering engineer, because that's the responsibility of the geosteering engineer to suggest the changes in the well trajectory. That's the main part of his job, to make decisions, to make geosteering decisions, and to send those recommendations to directional drillers. Of course, the responsibility of the driller to check the quality of the trajectory and to accept if this trajectory is drillable, if it's safe enough in terms of well quality and in terms of HEC to drill this trajectory. But the geosteering engineer has to completely understand how the trajectory is prepared, what it consists of, and how to work with it. So let's do a brief um, kind of review about what you can do with the trajectory as an geosteering engineer in the geosteering software. So let's start here from the well we've been using for the geosteering. So you see the two trajectories here, the planned trajectory and the actual trajectory, which is called here the active well. So you can look at them here in 3D, right? So the well always have a plan, or to say correctly, have a number of plans. So the plans have the versions, but always there is a one actual plan, which directional driller has to follow exactly at this moment. Okay, and also it has the actual trajectory, what is being drilled right now. So is what we have. Let's go back to our scenario. So, and you can see that that was our initial plan. And as we did before in the previous exercise, so we applied lots of changes on the trajectory. And now the actual trajectory is not following the plan anymore. But in this exercise, let's have a look how exactly we can work with the trajectory and what we can do with the trajectory using this steering software. For example, I'm using here the e-steering software, and it gives me the number of options to do with the uh, to work with the trajectory. So first of all, let's have a look at it in a digital format. For example, this is the plan. Let's have a look. This how it looks like. The main components of any trajectory is the measured depth, inclination, and azimuth. Having these three parameters, you can calculate the rest of it here, right? All these gray, all these gray columns are being calculated by the software. Okay, so once you have these three, you can calculate, or you can import it as the coordinate. So you can import MD and the coordinate, and the software will calculate the inclination and azimuth. So you can see this. Also the delta MD, you can see the dogleg severity, degrees per 10 meters. So it depends of the region, can be per 10 meters, can be per 30 meters, like 100 feet, it depends on the region. This is the tool phase, the tool of the directional driller which we're using to steer the well through vertical depth and through vertical depth subsea, also x and y of each point. So the true vertical depth subsea, you obviously know the difference. So it's the true vertical depth corrected with the calibration elevation. Okay, so that's the interesting thing here. So the software highlighting the points with the high dogleg severity here. So once we have a limit, the software highlights this line. So obviously we set it here as 1.7, the dogleg severity. So let's look at this trajectory in this driller's view, I would say. So that's the top view from north to south. That's the what we have here. So that's the this is x versus y, which like just the basic coordinates. So basically, this is the map view. This is TVD versus x. It's like a well profile. This is the TVD versus y, and this is the vertical section versus TVD. That's the favorite view of the directional drillers. Okay. So and if as you already seen, is how it looks like in the 3D. So we can just look at the trajectory, or we can use our surfaces to see how it looks according to surfaces. And we can also use the map, and this is our horizontal section, which is being drilled to this direction. Okay, so now let's go back to the trajectory planning tool. So let me do this. So imagine at this point we have to do trajectory change. So how are we going to do this? We have number of options. Number one, we go in here and we can do any changes manually. For example, Each survey contains of the surveys. Okay, so that's the surveys. Actual surveys being taken during the drilling. The bid projection, because as you know, the survey point is not exactly at the bid. The survey point is in the DNI package inside the MWD tool, and that's probably 10-15 meters ahead of the not ahead, above of the bid. Okay, and so in this we can consider here, and it has a plan. So what can we do? Number one, we can do the bid projection. If we want, we can do it manually, just as a matter of exercise. So I'm going to add the new line survey, and I want to see, for example, at this point, I want to estimate how can I get better back to the plan, or how can I, for example, stay in the formation. So let's try different scenarios. So number one, I'm just do it manually. So okay, the last survey was at 29 and the depth 29, 50, 59. So I'm going to put like 29, 80. And I will ask the plan to be built. Let's build it to 90.5, for example. And we keep the same azimuth. And the software is already calculated the dogleg severity. And pay attention to this picture here. So once I click save, we have this new point. Okay, and we can do this as many as we want. So let's say I'm going to 300 sharp, and now I want to be it already 91, and I save, and that's it. And that's how the geosteering engineers was used to do this in like years ago. Now it's more easy. For example, let me delete this one. So I can use my interactive tool here. Only one thing I have to be worried of is the dogleg severity. So in this case, now is dogleg is 1 per 10 meters, which is 3 per 30 meters, or 3 per 100 feet, which is quite aggressive, right? So let's imagine that directional driller told me you cannot exceed limit of 0.5 degrees in dogleg. That's fine. So let's shoot this one. Now this green cone is limited by maximum dogleg. So whatever I click here inside this green cone, it's not going to exceed the limit in the dogleg severity. Okay, so let's just go back. Let's clear this one, and now see. What if I want just to follow the formation angle? I would do this. I would use a minimum angle. I would go be more safer, go inside the middle of the pay zone. Okay, and we'll just soft and nicely finish my well. That's it. So the numbers all are here. Now I can just export this table, copy and paste, and send it to directional driller, or send it to my geosteering report. And I can choose different scenario. Like, for example, what happens if I will just keep drilling with 91? Let's do this. I'm here to hold. I can hold the angle, by the way. I can hold it, and or I can just put it manually. Let's do another one. Do it at 30, and let's put 91. 91. Save. Okay. So let's put another one. Let's just make it. Okay. And one more. Okay. So if I'm going with the angle 91, for example, I'm going to quit my formation exactly at the MD 3,099 meters, so it's almost like 3,100 meters. Okay, so what else we can do? We can do, let me delete this one. And like, what if I want to get back to the plan, right? So I'm not worried about the geology right now. So I just want to get to the plan as fast as I can. So we can do this, we can do that, and be done. That's it. Okay. Or I can use automatic option, which is also very interesting. Let me do this target, the plan survey. So I have to go back to my web. And I put my dog like a 0.5. Let's click build, and it's here. Or let me see, let me just make it more visible. So let's make it, I don't know, let's make it this color, a little bit thicker. No, it's not a good option. Sorry, we're going to make it black. Now it's good. Okay, so what if I try to do it in the automatic mode, plan survey, and now I put my dogleg as 0.1. Okay, and I do build, and I do save. And you see now it's the different picture, right? So it took longer for the trajectory to get back to this point. Or if I put, for example, very aggressive, like 1, build and save, and you see it's like almost immediately. So why all this exercise so important is for geosteering engineer to play with the trajectory, to estimate what he can do using this or that dogleg. So if he can go back to the formation, how fast he can back, what the meterage he will lose, for example. So all this is really important for the reporting. Okay, and then once he is ready, he can do adequate decision. Like in this case, I just want with the 0.5 as I've been instructed. I will just follow the phase zone and smoothly finish the well. That's it. That's the best I would do here. Okay. Okay. This is it for the moment. And that was the trajectory planning tool exercise for the geosteering engineer. Okay, so we're about to finalize the training, and here is the training summary, what we have learned from our agenda. Okay, so now we did the introduction to geosteering, and now we know what is a geosteering, that this is the method of steering the well inside the pay zone with the active correction of the trajectory based on the actual data and environment faced. Okay, so now we know why do we have geosteering, because the current technologies, tools, and calculation methods, they all have limitations, and that's why it brings errors and uncertainties. So, and if we let these errors and uncertainties be inside our wells and don't correct the trajectory based on the actual environment, so we're going to end up with the very poor result for the horizontal wells. Okay, so and to properly execute the geosteering of the well, we have the few methods available, from the basic ones to the most advanced. So the basic ones is the geosteering using non-azimuthal data. So you can have just one gamma ray curve and you can already do geosteering, and you can be quite efficient. So because the thousands and thousands of horizontal wells worldwide are drilled just with gamma ray only. So for more advanced BHAs, we can move to the azimuthal measurements, the azimuthal curves, and the azimuthal data for density, gamma ray, and resistivity, and we can generate borehole images which visualization, very useful visualization of the borehole cylinder lay down, and we can pick up the formation dips. We can calculate the angle of the dips, as we learn in the practice with the any software practice working with the images. And finally, the top edge technologies available for the industry right now is the direct deep and ultra deep directional measurements. So this family of the tool can provide depth of investigation up to 30 meters and more, right? So combining with the modern methodology to recalculate the seismic attributes, it can give you the picture like hundreds meters ahead of the beat. So also we have learned how to use the geosteering data to update our structural geological model and make it more accurate. So we use all the data available. We don't do only one single point update. We do multi-point update for all the data available. So we did a pre-job modeling and real-time data loading in the geosteering software. So now you understand the entire process from the beginning till the end, how it looks like. And also to support all this geosteering theory, we did a review for the LWD and DD technologies, logging while drilling and directional drilling, and also we touched a little bit measurements while drilling. So it's really important to refresh this part because geosteering engineer has to be has to be familiar very well with the technology, so he can communicate with the directional driller, with the logging well drilling engineer, and he can understand all the data which come in from all these sources. So here we summarize in our training. Thank you very much.